Welcome to Sundar's lecture. This is lecture number 60. In this lecture, we are going to take a numerical example. See, this is the numerical example. This is AC circuit. And in this circuit, we need to find what is the current through 2 ohms resistor using superposition theorem, Norton's theorem and Thevenin's theorem. See, we have taken so many problems using superposition theorem, Thevenin's theorem and Norton's theorem. Anyhow, we didn't take AC circuit problems in the examples. So, in this lecture, we are going to take this circuit, right? Before that, we try to get an overview of network theorems. Now, what are all the topics we have seen about network theorems, right? Because we are going to conclude network theorems with this lecture. So, we will just go through what are all the network theorems we have seen and what are all the ideas, basic ideas behind them, right? So, this is the first theorem. We have seen that it is, yes, superposition theorem, right? We have seen superposition theorem. So, what is the principle of superposition theorem? If we have a circuit like this, then what you need to do, you have to activate, if they are asking you to find what is the current in 3 ohms resistor, and then what you have to do, you have to activate any one of the source and then find what is the current in 3 ohms resistor, and then you deactivate this source, activate the second source and find what is the current in the 3 ohms resistor, and then activate the third source by and deactivating these two sources, then find what is the current in 3 ohms resistor, then sum up all the currents you got, and that is the final answer for current in 3 ohms resistor, right? This is how we would have solved a superposition theorem. Or we also told that you can also activate 2 sources at a time and deactivate one source, and you activate one source at a time and deactivate these 2 sources to find the current and add those 2 currents. Obviously, you will get what is the current through 3 ohms resistor. We have seen these kind of things. This is superposition theorem, right? And then we have seen substitution theorem. In substitution theorem, what we have done, we have solved all the we have solved this problem to find all the current in the resistor, and then what we have done with the current, we can replace this resistor by a voltage source. See, this current is 6 ohms and this resistor is 4 ohms. So 6 into 4, it can be a 24 volt source. That is what we have done here. Even you do this and you simplify the problem, again you will get the same current in all other branches. So, in substitution, or it may be we can do a voltage source, or we can convert that into a current source, or we can do, right? Or we can do, see here, we would have taken this both current and resistor as a 4 volt source. So, in substitution theorem, we can replace a resistor with a current source or voltage source, depends on the current flowing through the resistor. That is what we have seen, right? And then we have taken Norton's theorem. So, a circuit with a load resistor can be converted or can be drawn as an equivalent circuit like this. This is the load resistor, or we are calling it as impedances, load impedances, and we have to find what is the short circuit current and the Thevenin's resistor, Thevenin's impedance, and we can just connect like this, and we have derived a formula to find what is the current through this load resistor. That is what we have taken here, right? See, we have taken, this is the circuit we have taken. See, this is the load resistance, 4 ohms resistor, and then this is the linear network, and we have just converted this linear network to the equivalent Norton's network or Norton's circuit here. 4 ohms resistor, it is there and it is also here. Then we have found what is the current in the 4 ohms resistor using the formula whatever we have derived, right? So also we have told that if this load resistor is changing, then you don't need to find the current through this load resistor by solving the problem again. Just you have to substitute, instead of this 4 you put 6 if it is 6 ohms resistor, then you will get the total current through the load resistor. That is the real application of Norton's theorem or Thevenin's theorem. It can be anything, right? And then we have taken Thevenin's theorem, the same thing, same procedure, whatever the thing we have done in the Norton's theorem, We have just proceeded with a different, we have proceeded with the current there, now we are proceeding it with the voltage here, and then this linear network can be converted into the Thevenin's equivalent network. This is the Thevenin's equivalent network, and the current flow through this load impedance we have written like this, and we have taken another example, and we have found what is the current, right? That is what we have seen in the Thevenin's theorem. And then we have taken and we have told that it is not necessary to find the Thevenin's resistor or Thevenin's impedance by the procedure of simplifying the impedances. What we can do, this is also possible. So if you want to find what is the Thevenin's impedance, then what you do, find open circuit voltage and short circuit current, and then you divide it, you will get the Thevenin's impedance. That is also we know, right? And then we have taken a numerical problem with the dependent sources, and we have found what is the current through a particular resistor. And then this is the maximum power transfer theorem for DC circuit and AC circuit. For DC circuit, we have found that load resistance should be equal to Thevenin's resistance for maximum power transfer in the load resistor. This is for DC. And for AC, we have seen that this load impedance should be complex conjugate of the Thevenin's resistor, Thevenin's impedance. That is the condition for maximum power transfer in AC circuit. That is also we have seen, and we have taken a problem. See, we have derived this one. If this load resistor is purely resistive, then what is the condition? Then condition will be load resistor should be the modulus of Thevenin's impedance, absolute value, and that is also we have seen, right? Then yes, this is the expression for maximum power transfer. What is the maximum power transfer expression? Pmax should be is equal to VOC square divided by 4 RTH. In this case, RL should be is equal to RTH, or maybe ZL is equal to ZTH, right? We have seen this one, and then we have taken a problem, we solved it to find the maximum power transfer, and we have taken the another problem too, right? See, we have solved it. And then we have gone for Teligent's theorem. For Teligent's theorem, we have taken the basic idea of power delivered, power absorbed, and then we have formed what is the Teligent's theorem. In Teligent's theorem, you see, you have to take two different network with same topology, and the current voltage in this network in this branch and the current in this branch can be multiplied. Like that, you can multiply in all other branches. That should be is equal to 0. That is what we have seen, right, in Teligent's theorem, and we have applied Teligent's theorem. See, this is the network, and we have derived it with Teligent's theorem, and then we have applied Teligent's theorem in the reciprocity theorem. So in reciprocity theorem, what we have studied, see, this is the network 1. In this network, this is the voltage source, and here we have some resistors and load resistors has been connected. And what we are doing, you just take this voltage source, replace this with the other branch. I have replaced here, and if I want to find what is the current here, then in a single stroke I can find by using this expression, by using this combination expression. So we have seen that too. See, this is the network, and we have just transferred this voltage source to the other branch here, and we found this current by a single stroke, in single stroke. And we have seen many more in-depth concept in this. What is this one? In this reciprocity theorem. And then we have taken Millman's theorem. These kind of circuits can be converted like this, and what is the formula for those kind of things we have seen, and we have taken a numerical problem to find what is the current in 2 ohms resistor using Millman's theorem. That is what we have seen until today. And in this class, we are going to take this example, and we are going to find the current through 2 ohms resistance using these 3 theorems. Right, now we have taken this example. See, we are going to solve this problem by superposition theorem, right? So in superposition theorem, what we need to do, we need to deactivate one source, and then we have to activate the other source to find what is the current in 2 ohms resistor. Now what I have done, I have just deactivated this source now. This 25 at an angle of 90 degree, I have just deactivated. Now we need to find what is the current in 2 ohms resistor by 10 volt source only. See, this is a simple problem. So what we can do here, we just simplify, we try to simplify this resistor to find what is the total current, and if you know total current, apply current division rule to find what is the current in this resistor. So that is very simple. So we will do that. See how these resistors are connected. These two resistors are connected in parallel. So the equivalent resistance will be, maybe I will write it down. These two are connected in parallel and this is connected in series with this parallel combination. So to find R equivalent in this one, so it can be 3 plus 4j is connected in series with this parallel combination. So if you put in parallel combination, you need to add these two resistor and we need to multiply these two resistor. So if I simplify this, so I am getting R equivalent as 4.43 plus 4j ohms. Now if you want to find what is the total current, this current I, maybe I will write it as IT. So IT can be found by using what? What is the total voltage? It is 10 at an angle of 0 degree divided by 4.43 plus 4j, right? So if I simplify this, so I am getting 1.24 minus 1.12j. Now I know what is the total current. If I want to find what is this current now, what is this current, then I can write it as I through 2 ohms can be written as, see, I know what is total current, that is 1.24 minus 1.12j total current into opposite side resistor divided by total resistor 7 ohms. And it is simple now because this is a current division rule. We are just applying current division rule, right? So you have to do this one. And if I simplify this, so I am getting it as I through 2 ohms as 0.88 minus 0.8j amperes. This is by 10 volt source, right? Now what we need to do? We need to activate this source and we need to deactivate this source. Then what we need to do? We have to short circuit this. So I will draw the diagram. See, I have just drawn this diagram. So I have activated 25 volt source by deactivating the 10 volt source, right? Now what we need to do? Again same principle. I need to find what is the current in 2 ohms resistor. Then what I can do? These two are now connected in parallel with the 5 ohms resistor. So if I want to find what is R equivalent, then that should be 5 plus. These two are connected in parallel. So then it will be 2 into 3 plus 4j. 3 plus, maybe I am just considering this as the single resistor, right? Single impedance, and then it has to be 2 plus 3 plus 4j. Just sorry, we need to, sorry, I have made a mistake. We need to add in the denominator and we need to multiply in the numerator, right? So we need to add in the denominator. So if you are adding this one, 2 plus 3 plus 4j, and if I multiply, what I will get? I have to get 2 into 3 plus 4j, right? So this is the equivalent resistance. So if I find what is the equivalent resistance, I will just do. So I am getting it as 6.51 plus 0.39j, right? This is the equivalent resistance. So if I want to find what is the total current here, now I know what is the total resistance, maybe equivalent resistance. So if I want to find what is IT, I'm just considering it to be IT. So IT should be is equal to 25 at an angle of 90 degree divided by 6.51 plus 0.39j. So if I simplify this, so I am getting it as 0.23 plus 3.83 j amperes. So now I know what is the total current. So if I want to find what is the I through 2 ohms, this resistor current, then it will be total current, that is 0.23 plus 3.83 j. This is total current multiplication of, and what is the opposite side resistor? It is 3 plus 4j and divided by what is the total resistor? It is nothing but 3 plus 4j plus 2. So if I simplify this, then obviously I will get what is the current through 2 ohms resistor. So I am getting it as minus 0.57 plus 2.94 j amperes. So this is by 25 at an angle of 90 degree volt source. Now what you need to do, if you want to find what is the total current, then I through 2 ohms has to be addition of these two, right? So this will be 0.88 minus 0.8j and then this will be minus 0.57 plus 2.94 J. So if I simplify this, see, I am getting it as 0.31 plus 2.14 J amperes, and I have written this in as polar form 2.16 at an angle of 81.75 degree. So this is the current through 2 ohms resistor. See, that is what we have found. This is the same example we have taken for Millman's theorem, and we have found this as 2.15 at an angle of 81.63. But here I am getting 2.16 at an angle of 81.75 degree amperes. So this is how you need to simplify. Uh, Simplify, or means you have to find the current in 2 ohms resistor by superposition theorem. And now what we do, we try to find the same current in 2 ohms resistor by using Norton's theorem. Right? We will do that. So now you see, I have taken the same circuit and I have drawn the Norton's equivalent diagram. Then this is the formula, right? So IL should be is equal to IN into ZTH divided by ZL plus ZTH, and we know that we have given with ZL, right? This is 2 ohms resistor, and we need to find what is the current in 2 ohms resistor. That's just I have drawn this. See, to find IN, what we need to do to find IN, this is the circuit to find IN. So if you want to find what is IN, then you need to find what is the current through this short circuit branch. This 2 ohms resistor has to be short circuited, and if you short circuit this, you will get a diagram like this, and we need to find what is current here. See, this is very simple. You don't need to panic when this is happening like this. See, if this is short circuited, then the current should flow here, should not here. It cannot flow in this direction. This current by this 10 volt source should flow here, and this 25 volt source should flow here. Why? Because this is the short circuited path, low resistance path. So you can easily write IN can be written as 10 at an angle of 0 degree divided by 3 plus 4J, and then it has to plus this value 25 at an angle of 90 degree divided by 5. There is no other go, right? This current has to flow here, this current has to flow here. So it has to be added. That's all, because this is short circuited. If I have a resistor here, then I need to proceed with a different way. And this is how you need to find. So if I simplify this, I will get what is IN. IN, I can find it out as, so I am getting it as 1.2 plus 3.4J. Now what I need to do, I need to find ZTH. So how will you find ZTH? You need to open circuit this, and you need to find what is the resistance across here, and you need to short circuit the voltage sources. So I will draw the diagram. So I have drawn the diagram. See, if I want to find what is ZTH, these two resistors are connected in parallel, right? Both ends are connected. Then what I have to do? I have to add in the denominator 2 resistor, and I have to multiply in the numerator. This has to be done. And if I simplify this, so I am getting it as 2.5 plus 1.25 J ohms. Now you see, we know what is IN and we know what is ZTH. Just you substitute. So what you will get, IL will be is equal to, it is 1.2 plus 3.4 J, and I am just substituting in this expression into what is ZTH. It is 2.5 plus 1.25 J divided by what is the total resistance, ZL. So you have to add with 2 plus 2.5 plus 1.25 J. And if I simplify this, so if I simplify this, I am just getting IL is equal to 0.315 plus 2.13 J, and if I am writing it in the polar form, I am getting 2.15 at an angle of 81.58 degrees. So see, this is what we have got, right? Same answers. So now see, we have taken the same circuit to solve by Thevenin's theorem, right? So by Thevenin's theorem, if you want to solve this problem, then we need to draw the equivalent circuit for the Thevenin's theorem. So this is the equivalent network. So we need to find what is VOC and ZTH, right? To find the Thevenin's theorem, to find the current in load resistance by Thevenin's theorem. So how will you find VOC? So to find VOC, what you need to do, you need to open circuit this 2 ohms resistance to find what is the voltage here. So we will do that. So see, now we have drawn the diagram and we need to find what is the voltage between these 2 points. See, this is a single circuit, right? Maybe single circuit. So we can apply KVL here so that we can easily find what is the current. So I am just assuming current here it has I. Just apply KVL, single circuit KVL, so what you will get. So from minus to plus, it will be 10 at an angle of 0 degree minus 3 plus 4j, that should be into I, and then it is minus 5 into I, and then minus 25 at an angle of 90 degree, that should be is equal to 0, right? So if I simplify this one, this expression can be simplified as like this. It will be minus 3I, and then it will be minus 4ij minus 5I, and this can be written as minus 25I, right? Minus 25j, because it is 90 degree, right? So it will be, no, I am just writing it as it is. So it is at an angle of 90 degree, it is equal to 0. So if I simplify everything, if I simplify this, I will get I term. I have just simplify this and I will write it down. So see, I have just taken all these things. See, I have just derived it. Like these two can be added. So minus 8. So minus 4j plus 10 at an angle of 0 degree minus 25 at an angle of 0 degree. So I am just bringing these two terms to the other side. So you will get this as plus and this will be what? Minus, right? So I have just taken these two to the other side. So it will be like this. Now I can get I commonly outside. If I get I commonly outside, it will be 10 at an angle of 0 degree minus 25 at an angle of 90 degree divided by, what is this one? 8 plus 4j, right? 8 plus 4j. And if I simplify this, I will get, so I am getting it as minus 0.25 minus 3j amperes. Right, now you see, I know what is this current. So start from this point and go here, come here, voltage between any 2 points, right? We have seen these kind of things already. So if I want to write what is VOC, then it will be 10 at an angle of 0 degree. So the current is in the same direction as I am going. So I have to put minus, thus that should be 3 plus 4j. 3 plus 4j, I have to multiply, right, with the current. So if I multiply it with the current, what is the current? It is minus 0.25 and then it is minus 3j, that I have to close. So now if I simplify this, so I am getting it as VOC is equal to minus 1.25 plus 10 JV. So now you see, what is ZTH? That is what we have already found, right? I have already told you ZTH in Norton's theorem, and even if you are going for the Thevenin's theorem, both will be same. So I am just going to take the same ZTH, 2.5 plus 1.25. So ZTH I have already found, it is 2.5 plus 1.25 J ohms, right? I have already found this. And if I want to find what is IL, it is very simple, right? What is IL now? IL can be written as VOC, that is minus 1.25 plus 10J divided by, this is ZL. What is ZL? It is 2, right? It is 2 plus, and ZTH we have found it as 2.5 plus 1.25J. That's all, right? Now, if I simplify this, so I am getting it as IL is equal to 0.1315 plus 2.13J, and if I am writing it in polar form, I am getting 2.15 at an angle of 81.58 degree. See, this is what we have got in Norton's theorem and also in superposition theorem. See, I have solved this problem by three methods, right? One is superposition theorem, this method, and here I have solved it by Norton's theorem, and here I have just solved it by Thevenin's theorem. See, I am getting all the answers as same. So this is the procedure, and you follow this procedure, and we will wind up theorems in this class now, and we will take a new topic in the next class. So you go through all these lectures and solve more problems by your own. You try to solve the problems in AC circuit, because AC circuit have complex things, maybe 3 plus 4, 4 plus j, you will get j terms, imaginary terms, so it will be complex terms. So solving complex terms will be very difficult. So you solve many problems. You will get a good idea, right? So we will see in the next class. Thank you.